In this lesson, we'll continue our discussion of the three basic ladder logic instructions. Here are the three that we've been covering one by one. In this lesson, we'll be working with this one, which is probably the most misunderstood instruction of all. We'll use the name OTE, the abbreviation for Output Energize. And now for the main question, what does an OTE do in the program? Here are some of the most common ways that people try to answer that question. As you might expect, there are a lot of misconceptions and errors here, so let's come up with something more reliable. First of all, if true logic comes in, go write a 1. And if false logic comes in, go write a 0. Of course, we'll go through some examples to show you how this works, but first let's get rid of that confusing list. And now let's knock out one of the biggest mistakes that people make about the OTE instruction. Since it looks like the schematic symbol for a relay coil, many people tend to think of it that way. They imagine that the OTE is somehow wired up directly to an output device in the field. Some of this confusion comes from the official name Output Energize. That name is a very poor choice of words. Forget about energizing outputs and about the relay coil idea. Instead, concentrate on the fact that the OTE just tells the processor to either go write a 1 or go write a 0 into a bit box. Now let's work an example. Let's say that the processor comes across this OTE instruction in the ladder program. The address tells him that he's going to be working with the bit box named lamp E. We've got true logic coming in, and the rule says that the processor has to go write a 1. So the processor goes to the bit for lamp E and writes a 1 into the box. And now the processor is finished with the OTE for this pass through the ladder program. Now, just a few milliseconds later, let's say that the processor comes back around to the same OTE again. But this time around, something has changed the run conditions, and so now we've got false logic coming in. According to the rule, the processor has to go write a 0. The processor follows the address to the bit named lamp E and writes a 0 into the box. And now the processor is finished with the OTE for this pass through the program. And it really is just that simple. Let's work another. When the processor comes across this OTE instruction in the program, the address tells him that he's going to be working with the bit named O:001/1. We've got true logic coming in, and the rule says that the processor has to go write a 1. Now before we go any further, let's take a quick look in the bit ourselves and notice that there's already a 1 stored in that box. Get ready, and now watch the processor go to the bit, and once he's there, he writes a 1 into the box. Since a new 1 gets written on top of an old 1, you won't see anything happen on the screen, but the writing action does occur on every pass through the ladders. That's several hundred times a second. And now the processor is finished with the OTE for this pass through the program. Now before we do our next example, remember that the processor just wrote a 1 into the bit, and the 1 is still in there. Now let's say that before the processor comes back around to the OTE instruction again, we, the human programmers, sneak in behind his back and change the program. Suppose that this red X means that we're making an edit, and now we've just completely deleted the OTE instruction from the program. We'll show it grayed out on the screen to indicate that from now on, the processor will not be able to execute it. And here's a classic boot camp style question for you. What's going to happen to the status of that bit? Many beginners assume that the 1 will automatically drop back to a 0 since there's nothing to keep the output energized now that the OTE is gone. Let's take a closer look at this little animal and see why that very common answer is wrong. Many students are able to come to grips with the true go write a 1 part of an OTE. But the false go write a 0 part seems harder for most people to grasp. A lot of that comes from being taught incorrectly that the OTE works like a relay coil. That's wrong, because whenever you disconnect a relay coil, it de-energizes and it goes off. An OTE doesn't work that way. The old works like a relay coil explanation is a misguided effort to water down the OTE for beginners. The problem is that most classes taught that way never get past the beginner stage. The beyond beginner way to look at the question in this example is like this. Now that we've taken away the OTE instruction, there isn't anything left in the program to tell the processor what to do with that bit. The processor won't change the status of a bit without an instruction. So the correct answer is that the bit will keep its 1 status. Now here's another source of confusion. When most people hear the term true logic, they tend to think active or something's happening. And when they hear the term false logic, they usually think inactive or nothing is happening. That's the wrong way to think about the OTE instruction. Let's nail this down. First, look at what happens when the processor executes the OTE with false logic. The red arrow shows that the processor is actively going to the bit, and when he gets there, he actively writes a 0 into the box. Hold that thought, and let's compare it to what happens when the processor executes the OTE with true logic. The red arrow shows that the processor is actively going to the bit, and when he gets there, he actively writes a 1 into the box. And finally, suppose that the processor doesn't execute the OTE at all. In that case, nothing would happen. In other words, the processor wouldn't even go near the bit box. There are several ways to keep the OTE from being executed. Here's just one quick example using a jump and a label to make the processor skip right over the OTE completely. The key point is that false logic does not mean the same thing as no logic. An OTE with false logic makes the processor do something. It makes him go and write a 0, just like our rule says. Compare that to nothing happens when the OTE doesn't get executed at all. There's a big difference. Mistaking false logic for no logic causes more confusion and frustration than any other single misconception in PLCs. And here's something else to watch out for. Some of the official books use the term enabled instead of true logic. That part doesn't cause much trouble. Most people can accept that enabled means go write a 1. The problem comes up when the books and some instructors use the term disabled instead of false logic. This can be very misleading because most people naturally assume that the word disabled means that the OTE is not able to do anything. This is definitely wrong because an OTE being executed with false logic does indeed do something after all. Specifically, a false OTE always tells the processor to actively go write a 0. So, summing up, here's the OTE instruction, a command to the PLC processor. If true logic comes in, then the instruction tells the processor, go write a 1 into a bit box. Or if false logic comes in, then go write a 0 into the bit box. Naturally, the OTE always needs a valid address to tell it which bit box to go write into. The OTE works only on bit boxes located inside the processor, not on output devices in the field. This short video doesn't give us enough time to weed out all of the misconceptions on this list, but if anything here confuses you, we'll straighten it out when you get to the boot camp class. In the meantime, just keep this picture in mind and forget any beginner-level explanations that you might have learned before. So, here are the 3 basic instructions that we set out to cover, and here are the first 2 with their simple boot camp style rules. And now we're ready for the next lesson.